Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
Some of you may have been wondering about the assignment. That'll be posted this afternoon and it'll be due in 2 weeks. So I'll give you, I think, although it might have been suggested Tuesday, I'll give you till Friday of week 10. Today's Friday of week 8. So that's an assignment that covers chapters 1 to 6, but obviously an emphasis on the work we've just been doing about continuous random variables and transformations, that kind of thing, multivariate distributions. Pretty much that's the focus of what we've been covering recently. And very soon we'll be getting towards the statistical inference part of the course. And as you know, statistical inference is about making inferences, about taking data and trying to make conclusions from it. And because this is really orthodox mathematical statistics that we're doing using very classical techniques, that means there is a very big emphasis on the normal distribution, including multivariate normal distribution. Tells you pretty much all you need to know, actually, about handling multiple variables together if you assume the joint normality. So while that works perfectly in the situation where your data are in fact jointly normal, it also reinforces the importance of checking for normality or checking that normality is a valid assumption, because the inferences can be incorrect otherwise. So we'll be doing a bit more about the multivariate normal. Before that, I wanted to clear up a bit about maybe some other areas that we've gone past. The first one, I just want to go back to gamma and beta distributions in case there were, because these will come up quite a lot. In case anyone forgot, gamma, alpha, beta, where beta is this scale parameter that doesn't matter too much, has density x to the power of x, alpha minus 1, beta minus x. Normally it would be just minus x, but with a beta in it, you put x minus beta. That's if the scale is not 1. You have to fix it up. Gamma of alpha is the key thing. For those who forgot gamma alpha, you can get as the integral of the natural form of that. Forget this scale parameter. 0 to infinity. That's the complete gamma integral. And that, in case you forgot, gamma of n plus 1 is equal to n gamma of n. Although I've written that as if n is a natural number, that'll actually be true for any n that's positive. That recurrence will work, and therefore for integers we have gamma of n plus 1 is equal to n factorial if n is in the positive integers. So that's just a review. Gamma of alpha, I have to fix it up with a beta to the power alpha, because effectively there's one copy of beta for each x, and there's also another beta from the fact that a density sort of has the x in it. So that's fx of x. And then the expected value of x. Now you could do these through the MGF, and that's a perfectly fine thing. But I just wanted to show you that doing them through the integral form is not hard, and it's a great exercise in this thing where you use a known integral to calculate something. So if you want to do the expectation of x that way, all you do is you write that as integral of something that is known to be a density. If you can find something that's known to be a density, you're going to write alpha plus 1 minus 1, e to the minus x divided by beta. And that's always just fix up the constant so it's known to be a density. This is a classic trick. So gamma of alpha plus 1, beta to the power alpha plus 1, would be known to make that a density. Now, of course, I've lied because I've got the wrong constant. I've got to fix my constant by putting a beta on the numerator because I changed it from beta to beta plus 1. I also changed gamma alpha to gamma alpha plus 1. And as this little formula will remind you, that's true for any positive n, the factor that I've multiplied by going from gamma alpha to gamma alpha plus 1 is none other than alpha. So this has an extra alpha on the denominator. I should have an extra alpha on the numerator to cancel that out. So it's alpha beta times this. And then that is, in case anyone missed it, that is the density of gamma, not gamma alpha beta, gamma alpha plus 1 comma beta. So it can save you some effort to do that. So expected value of x is equal to alpha beta. Okay, so in case it was unclear, these things can be worth remembering because, as I'll remind you, chi squared with d degrees of freedom is exactly the same thing as gamma d over 2 comma 2. So that's a special case. Let's do the variance while we're at it. Well, just to cut a long story short, expected value of x squared, you'd have to do the same business, right? You'd have to integrate x squared, x to the power alpha minus 1, e to the minus x divided by beta dx. So the same thing, which is, if I had, this is x to the power alpha plus 2 minus 1, e to the minus x divided by beta, divided by gamma of, in this case, I'm just going to write what I want and fix it again. Beta to the alpha plus 2 dx. Now, of course, this integral, once again, is equal to 1, the integral. I should, in case of, yeah, the range of these densities is always x positive. I've never considered negative x's, so that's the integral I'm doing, the complete gamma integral. That one is 1, but I do need to fix up once again. I've got 2 powers of beta on the numerator, beta squared. I've also got, I should have gamma alpha plus 2 instead of gamma alpha. That amounts to a factor of alpha times alpha plus 1. So alpha plus 1. You can check that using, okay, so if anyone's worried about that, just double check using this equation star, and you can check that. So this is, alpha plus 1 beta squared. So that's alpha squared beta squared plus alpha beta squared, and times an integral that has the value 1. Okay? All integrals of density have the value 1. That's always the trick. So the variance of x, it works out very nicely, is of course expected value of x squared, and then I have to subtract the known mean squared, which is alpha squared beta squared. So this is nothing other than alpha beta squared. So if you have a gamma, we know its mean and we know its variance. Those are the two most important. We also know it's MGF for those who forgot. MTX equals 1 minus, and also a similar method for generating this 1 minus, I think it's beta t to the power minus alpha. And t, if you're being really pedantic, that would be for t less than 1 over beta, but that is well defined. So not for all positive t, but for enough positive t that it's a useful MGF. So let's go on with beta, and we saw when we were doing a bit of the transformations that there's a very close relation between alpha and beta. So let's now do the example of x beta. And since we haven't explicitly stated the mean and variance of this so far, we might as well do it while we're doing our calculations. Beta with parameters. I don't want to be doing subscripts, so I'm going to disappoint you by using alpha beta. So why would that be disappointing? If you just think conceptually, these are both shape parameters. That's kind of something I'll put in inverted commas. But so the alpha and beta are both very important in the beta case, like the two parameters. This is often called gamma alpha beta, but in the case of gamma, the beta is sort of a nuisance parameter. Its scale is just, it's effectively, you've multiplied everything by beta in that case, so it's less. So to remind you, in this case, this is shape, which is important, and scale, which I sort of consider very unimportant. Okay. So in beta, they're both shape parameters, and as you would recall, last time or maybe the time before, we were talking about how you got a joint beta gamma. Okay, let me not reuse X. Sorry, let me not reuse X. Let me call that to match last time U or V. I can't remember whether it was U or V. But last time we talked about if X is gamma alpha 1 independent of y gamma beta 1, then x divided by x plus y has the density, the distribution beta alpha beta, and also x plus y as a distribution gamma alpha plus beta comma 1. And those are independent. And so if we imagine this guy being called U, and the method for proving that was method 4, which is the transformation method. Transformation method with Jacobian. That's the calculation we did. So that was the first step, and then the second step was to integrate out over. Let's say that was U and that was V. Integrate out over dV to get density of U. So you could, to find a one variable distribution, it can be useful to go via a bivariate and then integrate out to get the density. It's because, of course, to get a marginal density, you take the joint density, then you integrate out the irrelevant variable, and that's how we do that. Okay, so that's a reminder of the relationship between beta and gamma. Let's now say, of course, Fu we found along that way. Sometimes people call it the beta function, but I'll try to write it without the beta function, which involves using gamma function. We got U to the power alpha minus 1, 1 minus U to the power beta minus 1. And importantly, this is on the range U from 0 to 1. So it's only a distribution on that interval. So depending on the shape. By the way, there are a lot of special cases of beta, including a uniform is a special case of beta. And it doesn't always look like bounded like that. It can also have asymptotes. If alpha is less than 1 or if beta is less than 1, you've got an asymptote in the density. Nevertheless, the formula is always the same. I should say, of course, alpha and beta have to be positive for the density even to exist. Gamma of alpha plus beta divided by gamma of alpha gamma of beta. Well, sorry, that's actually the beta function. So if I were to multiply that by... No, okay, so that expression is correct. That's the density. So let's go on. Now, I'll just remind you, this is a density, same gamma function, of course, as in the gamma case, for any constants that you choose, alpha and beta, that are positive. Okay, and that allows us to calculate the expectation and variance in the same fashion. It shouldn't be too surprising that it's how far along you are, so you might expect that if the expectation of x is alpha and expectation of y is beta, then you'd expect the u to be about alpha over alpha plus beta. That turns out to be true, but to prove it, you need to do the integral. So integral of u to the power, I'll just need to do u to the power 1 times u to the power alpha minus 1, 1 minus u to the power beta minus 1 du. Okay, 0 to 1. And then to make it a density, so it is same constant as before, gamma alpha, gamma beta. To make that a density, I'll need to fix the constant to be what it should be for we now think about the density of beta alpha plus 1 comma beta. To think about that density, we know that it should have gamma alpha plus 1 plus beta divided by gamma of alpha plus 1, gamma of beta. That's the way we think about it. Times u to the power alpha plus 1 minus 1, 1 minus u to the power beta minus 1 du. So that's the density. Now I need to fix it up because I changed the constant. I now need to put in the correct parameter because gamma of alpha plus 1, that has an extra factor of alpha, so I'll cancel that with an extra factor of alpha on the numerator. And gamma of alpha plus 1 plus beta, that has an extra factor of alpha plus beta compared to what I had here. By going from there to there, I added an extra factor of alpha plus beta. And so to fix that up, I have to put an alpha plus beta here. So that, once again, is, this is density of, and so we're always using the same trick that a known density integrates to 1. So that is alpha over alpha plus beta times 1. Okay? And to do the expectation of u squared, it's just going to get a little bit more gnarly, but you can still do it by the same means. Maybe I'll leave that as an exercise, and so finding the density, finding the variance of u can be done in the same method. So well, it is, of course, gamma of alpha plus 1 plus alpha plus 2 plus beta divided by gamma alpha plus 2 gamma beta u to the power alpha plus 2 minus 1, because you see I put an extra u squared times u to the alpha minus 1, so that gave me this 1 minus u to the power beta minus 1 du, and once again I need to fix my constant at the front. So instead of gamma alpha on the bottom, I had gamma alpha plus 2. That has an extra 2 factors, alpha plus 1. So I'd better cancel out those extra 2 factors in the by putting them in the numerator as well. Similarly, compared to gamma alpha plus beta, I had to write gamma of alpha plus 2 plus beta. That gave me 2 extra factors, alpha plus beta plus 1. So because I added those 2 factors in the numerator as extra factors, I have to put them in the denominator as well. And therefore, that's, once again, this is a density. So the trick gets used over and over again. So that has the value alpha times alpha plus 1 divided by alpha plus beta plus 1. And then that's expected value of u squared, and I have to subtract off variance of u will be the same thing, alpha plus 1 divided by plus beta plus 1. And then I have to subtract, of course, the square of what's the known mean. So it'll be something pretty complicated divided by alpha plus beta squared, alpha plus beta plus 1. And on the numerator, we may as well work it out. We've gone this far. So I have to do alpha plus 1, alpha plus beta, extra factor, and then subtract alpha squared, alpha plus beta plus 1 now. Just a little bit of algebra to get the final result. Alpha plus beta plus 1. An alpha cubed is going to disappear, an alpha squared beta is going to disappear, and a single alpha squared is going to disappear, and that means the only remaining term is alpha times 1 times beta. That's the only one that remains, alpha beta. So quite a nice simple formula in the end for variance of a beta. Okay, that's the end of that, and I hope rather than just learning your final formulas, you've noted that this issue of reusing densities comes up all the time, and pretty much any complicated integral you have to do, you should think about it, can I take a shortcut along these lines? Okay, let's go on with something else. It was mentioned in the textbook and the notes, but I think it's a very kind of easy proposition or idea, range-restricted distributions. I think in the end of chapter 6. So what is a range-restricted distribution? It's exactly what the name sounds like. And this is much easier than conditional distributions for continuous variables, because conditional distributions have the problem that to condition on a single point in a continuous distribution is conditioning on an event of probability 0, so there's interpretation issues. This has no such issues, which is just take a sub-interval, I, and a random variable x, such that of course, you want the probability that x lies in this interval to be positive. Then the conditional probabilities, probability of anything given x in that interval form the range restricted distribution of x. So there's, in other words, which is of course probability of that same event divided by intersect x in I, divided by probability of x in I. Because that probability is positive, there's nothing to do. The biggest example, or the biggest application, okay. By the way, let's do one example of that. If x is uniform, this is a really easy one, on an interval a to b, then the range restricted distribution of x given x is in the interval I is, it's still got to be uniform because, but the interval is now a, b, intersect I. Okay? So I could have had uniform on this interval, right? And let's imagine that I is a sub-interval of that. Or I doesn't even have to be a sub-interval, just gets a restriction. Okay. So if that's a to b, and then I have I here. So I just want to restrict to being in I. So that was the interval a to b. I have a perfectly normal uniform distribution from a to b. The range restricted distribution will be nothing other than, you will have a higher density because it's been restricted to a lower. So I'm plotting the density plots in this case. That is the d of x given x is an interval I. Now, I think this is not a super useful concept. The main use of it is something we already talked about, the biggest application, loss of memory property. We talked about this kind of in the context of functions that distributions that had a density. It had to be exponential. Sorry. It turns out you can have discrete loss of memory property states that for each little x, the distribution, the range restricted distribution of x given x greater than little x is the same, that's the loss of memory property, as the unconditional distribution of x. Okay, so of course when I say conditional distribution of x given x, I mean the conditional distribution, which is another way of saying range restricted distribution. Okay, so if this is true for all real numbers, x positive. We actually gave this argument before. It follows that x has a distribution exponential lambda for some lambda. Okay. If it's not true for all real, then it might actually. There are other examples. I'll just say otherwise variance of the loss of memory property could be true just only on the integers. In that case, you could get variance of geometric metric p are possible. Okay, so both geometric and exponential are distributions that in some sense have the loss of memory property, but the most comprehensive loss of memory property for all real x that are positive, that loss of memory property implies it must be exponential, not geometric. Okay, so that's all I want to say about range restricted distributions. As I say, I'm cleaning up a number of loose ends, so I just want to. This might be, since I'm doing that before we go on to chapter 7 in earnest. If anyone has any other topics they want us to cover, I would be most happy to do so. within what we've done. I have two other things I wanted to talk about, a bit more about normal and a bit about paradoxes related to conditioning. But at this point, since it's halfway through the lecture, I'll just ask if anyone else has any other requests. Because next week we'll be going on with chapter 7 in earnest. Okay, so let me do the, in the first instance, paradoxes related to conditional probability, conditional distributions. Okay, and they're ultimately you won't be surprised about these if you think back to that quote of Kolmogorov that I gave you, that it's the concept of a conditional probability with respect to an isolated event of probability 0 is an inadmissible concept. So it's about that isolated event of probability 0. So this is quite a famous one. Let's think about, now I know we haven't talked about distributions on shapes in 3D or anything like that. We've only talked about distributions on the whole of n-dimensional space. But nevertheless, you can, since it's just a paradox, not something we'll be doing calculations about, you can just imagine this, and it's quite practical because let's talk. I think some people call this a Simpson paradox, sometimes called a Kolmogorov paradox. But so let's think about the globe, and as you know, conventionally the globe is described with latitude, which tells you how far from the equator you are in angular terms, and longitude. And longitude, of course, doesn't measure distance from the equator. It measures some kind of angular rotation that you've gone from the meridian, which is the Greenwich Mean Time meridian traditionally, but from some fixed meridian. What is a meridian? A meridian, I guess there's a couple of terminologies that are used. You have the north pole of the globe and you have the south pole of the globe. And the meridians are any great circle that passes through the north and the south pole. They're the meridians. A great circle, if you don't know what that is, it's the analogue of a straight line. A number of definitions. One is that if you're only allowed to go on the surface of the Earth, of course we can't go inside the Earth, if you only go on the surface of the Earth, the shortest distance between 2 points is a great circle. It has to be. Another way to describe it is it's any circle whose centre lies on the centre of the Earth. So notably, there are a lot of circles on this picture whose centre does not lie at the centre of the Earth. Any circle of constant latitude is not a great circle, except for the equator. You see that? So this is the equator. And the equator is a great circle, but no other circle of constant latitude is a great circle. By contrast, all the meridians are great circles. Now, you might want to ask, given that I lie on a great... So, first of all, let's pick a random... Imagine you have one of those globes that can be spun in multiple directions. Maybe it has two hinges, and you just imagine spinning this globe so that every orientation is equally likely. So, not just spinning, fixing the poles, but I'm allowing the poles to move around too. There are some quite advanced globes you can buy that will allow it to spin like that. And I'm trying to make every configuration equally likely. And then I just pick a point uniformly at random according to that on the Earth's space. So another way to say that is every area, every single acre of land on the Earth's surface, including sea and land, is equally likely to be picked. That's another way of saying pick a uniform point at random on the globe's surface. Now we say, given that I do that, let's suppose that it lies on a given great circle. For instance, we could ask, given that the point lands on the equator, what is the conditional distribution of that? Given that it's on the equator, or if you don't like the conditional distribution, you could ask conditional expectation of a certain value, like conditional expectation of the longitude, something like that. But let's just concentrate on what is the conditional distribution of the point, given that it lies on the equator. Now, there seems like it's sort of an obvious answer. Does anyone have an obvious answer in mind? I picked a random point, and now, given that it lies on the equator, what's the distribution on that equator? Did you say the word uniform? Sure. Yeah, I think that seems very reasonable. So, take P on the Earth's surface uniform according to area at random. So uniformly at random by area. Okay. Given P lands on the equator, its distribution would seem to be, you would assume, uniform on that circle. Okay? So, in other words, the corresponding latitude, so the latitude equals 0, the random longitude, L, would have the distribution, if you're wondering what it means to be uniform in the circle, the longitude would have distribution uniform from 0 to 360 degrees. Or sometimes they do it plus 180 to minus 180, but let's say it's 0 to 360, that would be the random longitude. Okay, but now let's ask a totally different question, or apparently totally different question. Given P lands on the Greenwich meridian, now just for one moment, of course it's true that a meridian is only half a circle, so meridian, by the way, that's, I'll just imagine that is longitude equals 0. The latitude has the distribution these are, I'm not going through this fully mathematically because as you'll see there is a paradox in how we formulate it, but you'd say that the latitude has a distribution. Well, is it more likely to be near the equator or near the poles? Well, it seems to be vanishingly unlikely to be near the poles, right? Because there's only a very small area near the poles. And yet it seems to be quite likely to be near the equator. And in fact, if you follow that course of action through, you would say that the conditional distribution of the latitude should be distribution with density. Those who know a little bit of trigonometry can figure this out, because a rectangle here at height, at latitude, let's say the latitude is an angle theta. Remember, theta can be theta, which is in the interval minus 90 degrees to 90 degrees. That would be the conventional way of saying the latitude. If you go here theta, then the area of this, and then there is of course also the angle phi, which is the longitude. So remember phi, there's an angle phi there which comes from the axis. So if that's phi, then the area, from trigonometry we know this is actually r, well r is the radius. And then I have to talk about d theta, d phi, but also how does it vary with theta? If theta is 0, then you get 1. If theta is 90 degrees, you actually get times 0. There's no area at the North Pole. It goes down to 0. It's actually cosine theta, d theta, d phi. D theta, d phi. So I'm not going to justify that, but you can go back to your multivariable calculus if you want a proof of that. It's quite, it's a fact about circle, a fact about spheres. So cosine theta. Now, if you just think about that, the density is, what is the density of theta? I've integrated out over all phi, so the density should be cosine theta d theta, and theta is, in this case, less than pi over 2, translating, and greater than minus pi over 2, translating to radians. But I'd better put in a factor so that this integrates up to 1. As you may know, the integral of cosine is sine, and it's going from minus pi to pi, so that'll be a range of 2. So I should do 1/2 cos theta d theta. So that's a perfectly good density function on the interval minus pi over 2 to pi over 2. Okay, so i.e. certainly not uniform. Okay. And so it's true that that Greenwich meridian is not a great circle. So thus, it would seem that well, let's say given P lands on, let's extend that Greenwich meridian to make a great circle, because after all, it's a semicircle. It's half of a great circle. I'll just extend it around the other side, which involves incorporating also the international date line. Let's now ignore the fact that the international date line is not straight. You know, it zigzags a lot. So whatever the international date line would be if it were straight, that would be the latitude, that would be longitude equals 180 degrees, so just that straight line. Let's extend this over here. So we get a paradox. So the green on, on the great circle, so which I've written in green, of longitude 0 or 180 degrees, right? So 0 degrees would be the front part of that circle, 180 gives you the back. So given that your P lands on it, well, it's the same on the front and the back. The conditional density of latitude theta is, once again, half cosine theta d theta. It's the same conditional density 1/2 less than theta less than pi over 2. And you would be 1/2 likely to land on the front versus the back. So I'm now going to draw these two conditional distributions, and you can see that they're not the same. Well, it's pretty clear that they're not the same. Let's, on the red circle, you've got uniform. So whatever that is, you could imagine it as a strip that is kind of uniform, like a band. Just a piece of paper that's uniform all the way around. That's the red one. And yet the green one is not uniform all the way around. If I condition to lie on this great circle, which consists of the Greenwich Mean Time and its opposite, meridian, I have some kind of conditional distribution which is vanishingly unlikely to land at the poles. In fact, it actually has density 0 at the poles. It gets a bit more likely around the front. So I'm trying to illustrate the likelihood which gets larger towards the front, and then actually nothing at all at the poles. And then once again it gets a bit wider and wider towards the centre. But so this is proportional. That's proportional to cosine of theta. That's the width. So that conditional distribution is not the same as this. And what's the paradox? The paradox is, let's just step back a bit. I've said, given that it lies on a certain great circle, it should be uniform on that great circle. And then I took a different great circle, but all great circles are the same geometrically. You can rotate any one great circle onto another great circle. On this great circle, which is the same geometrically, but the conditional distribution I got is not at all uniform. It's much more likely to be at the equatorial parts and much less likely to be at the poles, and has density 0 at the poles. So they're not the same. That is, I think it's sometimes called Simpson's paradox or Kolmogorov's paradox. And what is the resolution to the paradox? Well, if you try and write this out in mathematics exactly as foreshadowed at the start, just taking the naive definition of conditioning doesn't work, because P lands on the equator as an event of probability 0. There's 0 area at the equator. And there's 0 area on that great circle. Okay, so first thing is, it doesn't make sense just to divide by the probability of landing on the equator. But then we still have conditional distributions. We have to understand what they mean. We go back to Kolmogorov, who said you can't have an isolated hypothesis. So the isolated hypothesis would just be you land on a great circle. Instead, it has to be part of the distribution of a random variable. So instead of thinking just the isolated hypothesis of the equator, we think of the random latitude, theta, and as you know, it's sort of like a limit of conditioning that theta is in a small range from 0 to epsilon. So that is of course, the random latitude. I'm always using the letter. So and all of a sudden the paradox goes away if you think about, instead of conditioning on a point, conditioning on a very small interval. think of a very small latitude from 0 to epsilon. Then I have equal width of this strip all the way around the equator. Whereas if I can condition on a small longitude, I get something totally different. So condition on the longitude, okay, which I've often been calling L, although sometimes also called phi. Phi and L are the same here. L, which is in the range 0 to epsilon, okay, that would only give me the Greenwich meridian. If I want to include the opposite, I'll include this one as well. L is in the range 180 plus epsilon, or you could translate it into radians if you like. And all of a sudden the paradox goes away. The shape of this is a ring of uniform width the whole way around. The shape of this is not a ring, it's just two wedges that meet at 2 points. So there is a wedge here, and there is a wedge here, and they meet at 2 points. And so no matter how small you make epsilon, those look totally different. This is uniform width, that has wedges. And that's why. So the relevant random variables are theta and L. So even though theta equals 0, so I'll write that here to resolve, the resolution of the paradox. So even though the events L equals 0, let me say, or L equals 180, and theta equals 0, look the same as events. Okay, events, they're both great circles of the globe. Even though they look the same as events, they are very different as random variables, theta versus L. And so the density of, really you can think about the latitude and longitude, L given theta of L given theta looks very different, you know. And I'll remind you that is uniform in L. Very different to F theta given L of theta given L, okay, which is not uniform at all. This is also why we don't use the notation. I like to write it as a function of two variables because both variables are important. It's not like you're just conditioning on an event. F of L given theta equals theta of L. Because that makes it look like that an event. I'll even say that this event is irrelevant. When you're conditioning on this conditional variable, the event doesn't matter, it's the variable that matters. Okay, so I think we've said enough about that paradox. It's been resolved. And whenever you think about, why are these two conditionings not looking the same, that is the resolution to the paradox. So now, the last thing I wanted to talk about was a bit more about the normal distribution, the joint normal distribution. So let us, fleshing out, sorry, maybe some of you didn't get a chance to see that, so I'll keep that there. The key fact, well, one of the many key facts about multivariate normal distributions. Okay, so we had two definitions of multivariate normal, but the best way to think about it for simplicity is just that you have some underlying IID normals, and you put them together by linear combinations, and you're also allowed to add a constant, and then you get, what you get is by definition a multivariate normal. Now we're trying to go backwards. How do you get from an arbitrary multivariate normal, which can have covariances and such, and how do you get back to the independent case? Well, what I consider to be the surprising fact is, as before, which I called a corollary last time, but I think it's important enough to be the theorem in its own right. If multivariate normal random variables. So that's multivariate normal, random variables, also called joint normal. X1, X2, up to Xn are uncorrelated. Okay, so that's a short way of saying that covariance of xi, by the way, correlation would be the same, but xi, xj equals 0 for all I and j that are not the same, then they are independent. And you might be always worried whether I was going to give you that silly, useless form of independence that's pairwise independent. No, they are mutually independent. So this is the strong statement that we want. Now I said last time, and I said it was a corollary, but maybe let's go through it in more detail, because this is something that we'll use again and again. Okay, so the proof. There are underlying. Okay. Now there's going to be a couple of simplifications that I do first of all. Exclude any xi's that are constant. Constant is another word for deterministic. In other words, a random variable that has zero variance. A zero variance random variable. Now, I'm allowed to do that because constants are independent of everything. So those are going to give us no trouble at all. You might say, of course, they're not constant; they're normal. But technically, a normal with zero variance. Sometimes this is, if you want to have the framework including every possible covariance matrix. Sometimes you want variance 0, and then you would get constants. So you just exclude them because they're automatically independent. Okay. So I will assume that to have been done beforehand. And there are underlying random variables z1, z2, ... zn. Now I'm going to make the key here, unlike when I started, I'm saying n is the same as the number of x's. The number of z's and the number of x's is the same, such that x I equals sum j equals 1 to n a I j z j for all I. And, well, of course, the name of the zi's should have suggested it. Zi's are all independent of one another, mutually independent, normal, 0. Now, that was the first definition I gave of multivariate normal. Some other books might take that to be a theorem about multivariate normal, but we'll take that to be given. But the key thing we're trying to work about is why are they mutually independent? Okay? So, we can calculate well, certainly we could find the covariances. Okay, covariance of xi with xj. The bilinearity will make that easy for us. Oh, people didn't object yet, but I've made something slightly fast and loose already, which is that I said that the zi's were ID normal 0, 1, and therefore centered. They're things that have mean 0. I said, in the first instance, I said that the xi's might not be centered. They might have a mean. But really, means, if xi has a mean, the independence of that will be the same as the independence of the corresponding centered variable. Because if x is independent of y, then x plus a constant is independent of y. So that's, rather than write that in words, I think it's this classic thing, WLOG, which if you haven't seen, that means without loss of generality, which always just makes our notation much simpler. Assume all xi's have mean 0. Okay, and we can do that. Why can we do it? Well, if they don't have mean 0, subtract the mean. It's still the independence of xi is the same question as the independence of xi minus mu1. Okay, so that makes our calculations a lot simpler. We don't need any means. We just have some constants times those variances. So we can find covariance of xi, xj is the sum of j equals 1 to n of, let's not do xi, xj, let's xi, xk, of a, I, j, a, k, j. So that's kind of like a dot product. Now, how is that the case? You just go through using the bilinearity of covariance. And the only ones that are going to pick out are when zj goes with zj. If zj goes with something that's not zj, then they're independent because of because of this. Okay? But not only we can find that, we can also find the joint density of x1 up to xk using, I can keep calling it method 4, which is obviously not something that extends beyond this course, but I called it method 4 at the time. This is the Jacobian transformation. This is what happened when we talked about a multivariate transformation, and the key thing is that